Now we go with the module 2, elastic properties of materials. In this we go with the bending of beams. Expressions for rectangular and circular cross sections of the beams. Bending of beams. What exactly is the bending of beams? A beam is a homogeneous body of uniform cross section whose length is large compared to other dimensions. You can see here it is a beam whose length is large compared to the other dimensions. Now here the diagrams you can see what is a beam. You can see the types of beams. Here A, B, C, D, E, F, it is a beam having a neutral axis. We will see what exactly is a neutral axis. A beam is a thin rod whose length is very much large compared to the other direction. Now a beam can be imagined to be made up of longitudinal filaments. You can see here in the diagram, in the center diagram, you can see A, B is one filament, C, D is another filament, E, F is another filament. Now under the application of the load, the upper filaments will be undergoing extensions and the lower filaments will undergo compressions. You can see in the rightmost figure, when you apply the force on both the ends of the beam, you can see that AB has been increased and EF, E dash, F dash has been reduced. That means upper part will be expanded and the lower parts will be compressed. There exists one filament where it do not undergo either expansion or compressions. So that layer is called as a neutral axis. The filament that does not undergo any change in dimension is nothing but the neutral axis. If you look at the figure over here, A, B, when it is been bent, it has come to A dash, B dash extensions, and E, F has become E dash, F dash. It is nothing but a compression. The one which is not been either expanded or compressed is nothing but CD. That means CD is the surface which is not at all expanded or compressed. Therefore, it is called as a neutral axis. So, the filament that does not undergo any change in dimension is the neutral axis. So, here CD is the neutral axis. You can see from the diagram. Now, you can see that beam here, which is nothing but a L whose length is large compared to the other dimensions. Next we see with the neutral surface or the plane. Neutral surface or the plane is a layer of uniform beam which does not undergo any change in its dimensions when the beam is subjected to bending within the elastic limits. What it says here is a layer in the uniform which do not undergo, we know that neutral axis which do not undergo any change in its dimensions. So then that surface, that layer is neutral axis, that axis is neutral axis, and that plane of uniform beam is called as a neutral plane. Now what is meant by bending moment? Bending moment of a beam is defined as the total moment of forces acting on the upper and lower layers or surfaces of the beam. So bending moment is nothing but the amount of total amount of force acting on upper part or the lower part of a beam, upper and the lower surface of the beam. Upper part is extension and lower part is compression. Now total moment of force acting on upper and lower surface of the beam is called as a bending moment. Now we see the expression for a bending moment of a beam. Consider a uniform beam can be thought as made up of large number of layers A, B, C, D, E, F. From the figure A, you can see from the figure A, it is a beam having AB is the upper filament, CD is the middle filament, and EF is the lower layer of the filament, or we can say layer or a filament, whatever it is. Now under the action of external couple, section is bent into an arc. You can see when you bend both sides of the beam downwards, the resultant appearance will be in the figure B. You can see over here. Under the action of external couple section, it is bent, section is bent into an arc. That part has been bent into a form of an arc. Here layer CD is the neutral surface where there is no change in the length. And layer AB is above the neutral surface is elongated by A dash, B dash. And layer EF is below the neutral surface is contracted to E dash and F dash. Beam is bent into an arc of circle of radius capital R. You can see the capital of radius R from the D to O. is nothing but capital R. It is clearly shown in the diagram. O to D is nothing but capital R. It is the radius of the arc. Now CD is equal to R theta. From here we can say that CD is equal to R theta because it is a common angle subtended at the layers at O. If you can see from the figure, tan theta is equal to CD by R. Therefore, theta can be taken as, the tan theta can be taken as theta. So, therefore, CD is equal to R theta. You are getting that equation because it is a common angle subtended at the layers O from the neutral axis. Now, elongation AB. What is the elongation AB? Change in the length, that is final position minus initial position, that is A dash B dash is the final extension and AB is the initial one. So A dash B dash minus AB. Before bending, AB is equal to CD is equal to R theta. Each layer of the beam is separated by a distance of smaller. You can see from the diagram here, from the D neutral surface to the B dash, the layer is separated by a distance of smaller. The same thing we are taking in this slide. Each layer of a beam is separated by a distance of smaller. So after bending, it is A dash B dash. Therefore, it can be taken as capital R plus small r into theta, which is nothing but A dash B dash. Therefore, change in the length is R plus R into theta minus R theta. That is capital R plus R small r into theta minus capital R theta, which is nothing but small r into theta. Let that be equation 4. Now, original length is nothing but R theta. Original length is given by R theta. From equations 4 and 5. From equation 4 and 5. We know we got from 4 is nothing but the change in the length and original length is equation 5. We know that linear strain is equal to R theta, change in length by original length. Getting the values from equation 4 and 5, we are getting small r by capital R. Let that be equation 6. As y is nothing but the Young's modulus, which is nothing but longitudinal strain by y is a Young's modulus given by longitudinal stress by linear strain, and rearranging the terms, longitudinal stress can be taken as y into linear strain. Longitudinal stress is nothing but F by A, which is equal to y into small r by capital R. It is just a rearranging of the terms. So again, F is equal to YAR by capital R. YA small r by capital R. It is equation 7. The moment of force about the neutral axis. We know that moment of force is nothing but about the neutral axis is force into perpendicular distance, which is nothing but F force is nothing but F, and perpendicular distance from the neutral axis is taken as small r. Therefore, we are getting as F is equal to YA by capital R into R square. Here we are getting this F value as, from this equation 7 we got it as F is equal to YAR by capital R. The same we are substituting here in this F into R, YAR square by R. You are getting the equation 8. Now, so moment of force acting on the entire beam is a summation of all the moment of forces about the neutral axis. So it is summation of YA small r square by capital R. So Y by R is remaining constant. We take it as summation of AR square, as here the moment of inertia of a body about a given axis. Summation of A into small r square is called as geometric moment of inertia, which is termed as IG. Therefore, IG is taken as summation of A into small r square, which is nothing but AK square, where A is the area of cross section of the beam and K is the radius of gyration about the neutral axis. From equation 9 and 10, we can say that moment of force is equal to Y by R into IG. From equation 10, we have seen that IG is nothing but summation of AR square. Substitute the same thing in equation 9. So, moment of force is nothing but Y by R into IG. That means the bending moment of the beam is nothing but Y by R into IG. It is equation 11. Now, expression for bending moment for a beam of rectangular cross section with breadth B and D is the thickness of the beam is given by Y by R into BD cube by 12. So expression for bending moment of a rectangular cross section. B is the breadth and D is the thickness. It is given by y by r into b d cube by 12. It is only the expression for you for this. And next is expression for bending moment of the beam of a circular cross section with rho is the radius given by pi y by 4r into rho cube, rho to the power of 4, sorry. So bending moment of a beam of circular cross section is given by pi y by 4r into rho to the power of 4 is the bending moment for the circular cross section. Thank you.